Welcome back. Today we're going to talk about a thing that is very common in our lives, in our everyday lives, which is sound. So sound, as you probably heard before, is a wave. And because it's a wave, it has so many characteristics that we've already looked at that waves have. So the first one is we can determine if it's a longitudinal wave or it's a transverse wave. So maybe you remember from the waves class that sound is one of the few things that we commonly see that is a longitudinal wave. So we're going to define sound as a longitudinal wave. And what causes this longitudinal wave? It's always caused by a vibration. So we can say sound is a longitudinal wave caused by a vibration. So you've seen, for example, a guitar. When you pluck a guitar string, the string vibrates and that generates a sound. When you play a piano, pianos also have strings underneath them that vibrate and generate the sound. But right now I'm producing a sound with my voice. So what is vibrating in that, in this example? Vocal cords. So vocal cords are strings that we have in our throats that vibrate and generate the sound that we speak with. Your speakers, you can see that they have this little membrane that vibrates. So we know what causes the vibration, but how does the vibration from the sound source get to our ears and make us hear things? Well, that's because the vibrations travel through a medium. So how could my voice travel from my mouth to the camera? It moved the molecules of air longitudinally until they reached from my mouth to the microphone. So you can see here an image of how the sound source makes the molecules vibrate, get closer and farther away from each other, such that the sound travels. So that means that if you have a case in which there's no air, then sound doesn't have a medium to travel through, so it can't travel. So in space, for example, there's no air, there's nothing that vibrates, so astronauts can't hear each other. You see that astronauts have their spacesuit and they talk via a radio. Radios, if you remember, are electromagnetic waves. They're transverse waves and they don't require a medium. But normal sound of speaking does require a medium. So that's why if astronauts shout in space, and they don't have a radio, they're not going to hear anything. That's why we don't hear the sun, even though it has very powerful explosions happening on its surface every second. So sound is a longitudinal wave caused by a vibration that requires a medium. So let's start looking at the characteristics of waves that sound have to have as well. So all waves have a speed. What is the speed of sound then? We've talked about the speed of light, but not about the speed of sound. So the speed of sound in air is usually around, so this means about 343 meters per second in air. But because the waves have to travel in a medium, the speed is different if you're not in air, but in water or through metal or through a wall. So there's different speeds in different mediums. So for example, the speed of sound in water is about 1,500 meters per second. And in metals, the speed is about 5,000 meters per second. Because sound travels much faster in metal, and the train tracks are made of metal, people put their ear to the train track, and they could hear the train even if it was more than 10 times farther than what you could hear regularly in the air. In general, you just say that the speed of sound is 343 meters per second because air is the medium that we care about the most. Hopefully you remember, when we have a wave traveling in time, it goes up and down, up and down, up and down, right? And we have two things that we can talk about. We can talk about the amplitude of the wave, which is how high the peaks are or how low the valleys are. And we also have the frequency, which is how many peaks or how many valleys pass by per second, how many waves pass by. So what does that mean in terms of sound? Well, amplitude actually is what determines the loudness. or the intensity. So it's proportional to the loudness, how loud you hear it. This is also called intensity of the sound. It's measured in a unit called decibels. Maybe you've heard about it. So the unit is decibels. And this determines if a sound is bad for our ears or not. So sounds greater than 120 decibels are dangerous for us. To compare, about 70 decibels is the sound of someone talking in front of you. So this is conversation. And this is if you're in an airport really close to an airplane and you hear the airplane leaving the airport, that would be around 150 decibels. So that's amplitude. And what does frequency determine? Frequency determines pitch. In Spanish, this is called tono, right? So the greater amplitude, the louder you hear. The greater the frequency, the higher pitch. A note with a low pitch would be that means it has a low frequency. A high pitch would be that is a high frequency. That first note is probably something like this, and the first note is something like this. Higher frequency, higher pitch. The unit of frequency is hertz. So I put here a list of common frequencies for common animals. I started with humans. The range of frequencies that a human can hear is around from 20 to 20,000 hertz. However, this gets a lot smaller with age. So old people can no longer hear 20,000 hertz, and maybe by 80 years old they hear only until 5,000 hertz. So below and above this range, it's not dangerous. More decibels is dangerous, more frequency just means we can't hear it. Actually, above this range, it's called ultrasound. If you've ever heard of the medical diagnostic system, ultrasound, that just means that it's bigger than 20,000 hertz. That's why when you get an exam, you don't hear it, but other animals might. So for example, cats and dogs have approximately the same range of frequencies that they can hear. It's about 60 to 50,000. So they can't hear the really low sounds that we can hear, but they can hear a lot more higher frequency sounds. And bats, they have actually a much higher range of frequencies that they can hear. They can hear from 10,000 hertz to about 100,000 hertz. So many times they're communicating with ultrasound, sounds bigger than 20,000 hertz, and we as humans know nothing about it. Because sounds are waves, they exhibit the 4 wave behaviors that we've learned about before. They exhibit reflection, refraction, diffraction, and interference. 2 specifically have very noticeable effects. Reflection would be an echo. When you scream at something and the sound reflects back to your ears, you hear it again, that's called an echo. Usually you can't hear your own echo because the reflection is so fast that you can't distinguish the first one with the second one. But if you're in a place that has really far away walls that have really good acoustics, then you can actually hear your echo because you hear the second time completely different from the first time. And then diffraction, the other behavior we learned before, is why we can hear sounds around corners. So if someone is in another room with the doors open, the sound will move through, bend through the corner, and reach the other person, even if he's not in a straight line with me. The regular wave equation that we've used and the motion equation are still valid for sound waves. So we have this one, which is speed is wavelength times frequency. That'll probably be useful for today. And distance equals speed times time. And finally, we're going to talk about the Doppler effect. Doppler effect, maybe you've heard that before. So Doppler effect is defined as a change in frequency when a sound source, like a speaker or a moving car, moves relative to an observer that is standing some distance away from the source. So let's write that down. Here it is. So change in perceived frequency when a sound source moves relative to an observer. So basically what this means is you have a source that is producing sound, and we have an observer somewhere over here. It doesn't matter who's moving. Either the sound source is moving or the person is moving. Either they're moving towards each other or they're moving away from each other, or they can both move. The important thing is the relative motion. So if anything is moving but they're getting closer together, the observer will perceive a higher frequency than if they were both standing still. If they're moving apart, the observer would perceive a lower frequency than if they were standing still. So let's write that. Yeah, so basically if they're moving towards each other, there's a higher frequency perceived, and if they're moving apart, there's a lower frequency perceived. A second ago, we talked about frequency determining pitch. So this means that when a source is moving towards you as an observer, you hear a higher pitch. If it's moving away from you, you hear a lower pitch. So maybe you've been in the street and you hear an ambulance, and you hear that it goes from a higher pitch, a higher tone of a note, to a lower tone when it passes by you. In the case that the source is moving at a higher speed than the speed of sound, it's going to already have passed the first wave when the second one is made. So it's going to look like this. So it creates the first wave. And then when it creates the second wave, it's already out of the first one because the waves, the motion is faster. So it's going to look something like this. What happens is that the person that hears this is going to get this giant cone of added up waves that are called a sonic boom. You've probably heard about this, but these airplanes that move faster than the speed of light, if they pass by you, first you see the airplane pass by, and afterwards, when the sonic boom reaches you, you hear this loud pop. So basically, this sonic boom is generated when the source moves faster than the speed of sound. So that means supersonic. And that's it for sound.